Good morning, it's Kitty the Crazy Math Nerd back again for another video on optimization. So this is just an introduction to optimization, so we'll be doing some of the easier problems. In part two, we'll get to some more of the difficult problems, but this should get us started. So in optimization, when you have a problem that requires that, you'll see words like maximum or minimum or the smallest or the largest. And so when you see things like that, that's a little hint that you're probably going to need to use the steps that we're going to use today to find to optimize the problem. So normally in this, they'll ask you to maximize or minimize something. And then they'll tell you something else that has nothing to do with that, and you're going to have to manipulate that to help you find your maximum. So for example, this says, given that the sum of two numbers is 11, what is the maximum product of those two numbers? Well, this is so kind of strange because it doesn't tell you what to call the numbers or anything. So the first thing you have to do is pick two numbers, and I'm going to pick X and Y as my two numbers. And you need to write down the thing that you are trying to maximize or minimize. So I'm trying to maximize the product, and we normally use use letters that represent whatever is in the problem. We do that a lot more than we've done in the past. So product is X times Y. Well, I'd love to take the derivative of this, but there are two variables. So what I'm going to do is I'm going to write an extraneous statement that I'm going to pull from the problem. So it says, given that the sum of the two numbers is 11, that has nothing to do with the product, but that's going to help us get this thing that we're trying to maximize or minimize in terms of one variable. So let me write that statement down, that the sum of the two numbers is 11. So this extraneous information allows us to solve for one of the variables, and I'll just solve for Y. So Y would equal 11 minus X. And then you're going to come over here, back to your thing that you're actually trying to maximize or minimize, and you're going to put that in for your Y. So your whole goal is to get the thing that you're trying to maximize or minimize in terms of one variable. Then you can take the derivative, set it equals 0, and see if it is in fact your maximum or minimum that you want. So this is just kind of thinking about this, this is a negative parabola. So it is going to have a maximum of it, right? But let's just act like we don't know anything, we don't know anything about graph or anything. So I'm going to actually multiply this together. So it's 11x minus x squared. And I'm going to take the derivative, and that's 11 minus 2x. And I'm going to set that equal to 0. And when I do, I get x equals 11 over 2. So the first number is 11 over 2. That is the first number that the sum of the two numbers is 11, and the maximum of the two numbers is, that the product is a maximum. So that's my first number. Maybe I should have picked an even number so this would go a little better, but I just was making up an example. It doesn't matter. It doesn't have to be nice numbers. 11/2 is a number too, right? But we have to find both of the numbers. So and it says, what is the maximum product of those two numbers? So let me find the other number. Let me answer the question, because it does say, what is the maximum product? If it said, what are the two numbers, I would have to find both of the numbers. It didn't really say that. So actually, at this point, I can just plug 11/2 back into the product and find that maximum product, because that's what it said. So the product at 11/2 is going to be my maximum, and that will be 11, no, I'm going to put it into, I'm going to put it into this little guy right here, if that's okay. It doesn't matter. One factor form, one's not. 11 times 11/2 minus, oh, this is going to be fun. Of course, I should have picked an even number. 11/2 squared. And so that's 11 squared, which is 121. over 2 minus 121 over 4. And I'm going to multiply this by 2. That's 242 over 4 minus 121 over 4, which is 121 over 4, which I do not think makes a nice number, but that is the maximum product. And if we want to make sure this is a maximum, we can do a number line analysis just to check. So let's do that. Let's put 11 halves right here, and let's pick a number to the left of 11 halves, like 2 or 1 or 0, or 0 would be so easy, wouldn't it? Let's put 0 in there. You put 0 into here, well, you get 0. Maybe that's not the best one. Let's try, oh, I didn't put it back into the derivative. I'm so crazy. You got to put it back into the derivative. Yeah, got to put it back into here. So if you put 0 back into here, you get some positive number. And if you put, I don't know, 10 in, that would be some negative number. And so it is increasing to decreasing. And so that does mean it is a maximum. So your maximum product is 121 over 4. So the thing is, you've got to write down what you're trying to maximize or minimize. You've got to find an extraneous information about the situation that allows you to solve and put the thing you're trying to maximize or minimize in terms of one variable, take the derivative, set it equal to 0, and answer the question. That's the big deal. So if it says, what is the maximum product, I got to do that. If it says, what are the two numbers, I have to give the two numbers. Okay? This next example is very similar to it. This is from Master Math Mentor. It says, a rectangle has a perimeter of 71 feet. What length and width should it have so that the area is a maximum? And what is the maximum area? So this actually asks you two questions. So you're trying to maximize area of a rectangle. So the area of a rectangle is length times width. So that's the thing that you're trying to find the biggest of. So the next thing you do is you find what is the secondary. You must find that secondary equation. So you go find that extraneous information, and the perimeter is that extraneous information has nothing to do with the area. So let's write the perimeter of a rectangle, and that's 2L plus 2W and equals 71. Notice that you want to use, you might want to draw a rectangle and write W and L, and whatever you decide on these letters, you need to be consistent so that when you solve for one and put it in the other, it still makes sense. So it doesn't matter which one you solve for. I'm just going to solve for W. So W equals 71 minus 2L divided by 2. All right. So if you wanted to make that nicer, you could make it 71 over 2 minus L. That'd be fine. So we're going to put that over in our main equation. This is the primary or main equation, the thing that we're really trying to maximize or minimize. So I'm going to write L times 71 over 2 minus L. And I am going to distribute because that'll make it easier, I think. 71 halves L minus L squared. Okay, so this is the thing I'm trying to maximize or minimize, and I do have it in terms of one variable. So now it's time to take the derivative and set it equal to 0. So the derivative in terms of L is equal to 71 over 2 minus 2L. And that is equal to 0 when L is equal to negative 71 halves. And then I'm going to multiply by negative 1/2. Or divide by 2, however you want to look at that, and L is 71 fourths. Now this particular problem asks you to find the length and width and the maximum area. So I've got the length. I'm going to put the length back into this right here where we solve for W to find W. So the width is 71 over 2 minus 71 over 4. And again, we got to double that, 142 over 4. We've not had really nice numbers, have we? And 71 over 4 equals 71 over 4. Oh my goodness, look at there. The length and the width are the same. That is amazing. I wonder if that always works. So your length and your width, so the length is maximum when you're 71/4, and your width is maximum when you're, oh my gosh, 71/4. That is just crazy, nutty. I know, right? And so then it says, what is the maximum area? And the area is maximum at 71/4. And if you put that in there, you get 71/4 squared. Oh, wow. And that's, what is that? Is that feet squared? 71 squared, feet squared. I'll make sure I put the units on there. So that's my maximum area, whatever that is. And you get a calculator and make that a nicer number if you'd like to. That's very cool. Now, how do you know this is going to be a maximum? Again, guys, if you just think about what this is in the beginning, this is a negative parabola. So when you find this derivative equal to 0, you're going to find that vertex of that upside down parabola. If you want to go do a number line analysis to check it, that's fine. But knowing what I'm starting with, that this is a negative parabola, I know that this point I'm going to find is that maximum. Okay? All right, let's try another one. Oh, the river problem. Okay, a farmer has 2,000 feet of fencing to enclose a pasture area. The field will be in the shape of a rectangle. So, and it's going to be against a river where there's no fencing needed. What is the largest area field that can be created, and what are the dimensions? So the first thing you've got to do is label this picture so we can start talking. So I'm going to call this L, and I'm going to call this W, and there's another W. There is not going to be any fencing over here along the river. So the largest area field is going to be area equals length times width. We're still dealing with a rectangle, and that's the area formula for that. The extraneous information that we're going to use to actually get it in terms of one variable is going to be this fencing here, the 2,000 feet of fencing. So that would be around the pasture. And so notice that you have two W's, but only one L where you're going to need fencing, because you don't need two L because there won't be any fencing right there on the river. And that should be equal to 2,000. So you've got your primary thing that you're trying to maximize or minimize, and then you have this extraneous information that has nothing to do with the area, but we're going to have to use it in order to get this area formula in terms of one variable. All right. So we're going to solve for L because it's easy. So I don't have to divide by anything. I know, aren't I lazy? And I'm going to throw that in there. So the thing that I'm trying to maximize or minimize, which is the area, is going to be 2,000 minus 2W times W. And again, we're in this negative parabola situation. Boy, I feel like I've done this over and over again. Many of them are similar, so you kind of feel like you keep doing the same thing over again, or similar things. That's okay. You're not crazy. And so this is the thing I'm trying to maximize or minimize. So I'm going to take the derivative and set it equal to 0. When I do, I get W equals 2,000 over 4, which I believe is 50. So that's 500, sorry, hello. So that is the width and that's 500 feet. I find if I don't like start putting my units on here, I'll drop them and then I'll lose my units, and that's bad. All right, so now here it's very important at this point to go back and ask, what am I really finding, to make sure you answer all the questions. So it says, what is the largest area field and what are its dimensions? Boy, they just want everything from us. So they want the dimensions and the area. So I need to go find length, and usually when you go find one of them, you've already solved for the other one up here, so you just plug that in, and that makes it easier. Don't go reinvent the wheel. So length is 2,000 minus 2 times 500, which I hope is 1,000, and so there's 1,000 feet for length. And so I'm going to put my answer over here. I'm going to put it in green after. Oh, Christmas is coming on. So my width is 500. That's my maximum. My length is 1,000. And my maximum area is 500 times 1,000, which equals, I'm going to add 3 more zeros. 1, 2, 3. 500,000 feet squared. All right, so make sure that's a big thing, make sure you answer the question that is asked of you. That's the biggest thing kids forget to do. They forget to answer the question. All right, so here's probably my favorite. It's called the box problem. So we have an open box, and it is to be made from a piece of metal that is 16 by 30, and you're going to cut out squares of equal size from corners and bend the sides up. This is where you have to have some kind of visual, and I think on Master Math Mentor, which I did steal this from, there is a picture, but many times you won't have a picture. So we're going to have to draw one. Let's see if my Mobi will work and snap that into place like it's supposed to. Woohoo! I love that. All right, so now there's our 16 by 30. So I'm going to call this 16 because it's shorter, and call this 30. All right, so what they're saying is you're going to cut out squares, and when you do, you cut out these little squares, it'll make the box, it'll make this flat thing fold up to be a box. So your job is to figure out how much should I cut so that the box has the greatest amount of volume. So there are 2 questions. What size should the square be, and what is the maximum volume? So they're working you on this one too. So make sure you answer 2 questions when you finish. How much should you cut out, and what is the maximum volume? So the volume of a box is length times width times height. And so that is the thing that we're trying to maximize or minimize. But we're in real big trouble here because I don't know, that's 3 letters. So Lord, I don't know what I'm going to do. This is a little harder than the ones we've done because the other ones were like, oh, and here's the other thing I know, and then I'm just going to plug it in. This is a little tougher. So let's call this cut, because we don't know what it is, X. So if you think about it, if this whole thing is 30, and you cut X over here, and you cut X over here, then when you fold it up, this side will be 30 minus 2 x's. See that? Because you're getting an X from both sides. So what we're going to do is we're going to write the length, the width, and height in terms of the cutting of the box. And that's how you make this all in terms of one variable. So the length is not going to be 30. It's going to be 30 minus cutting both sides, cutting from both sides. Your width is kind of the same thing. You start off with a width of 16, but if you cut an X off of this side and an X off of this side, then the length that is left, it will be shorter right there, right? It will be minus 2X. And then the height of the box, if you fold it up, it will be X high. Okay? And so this is the point where you might want to grab a graphing calculator. You actually can do this by hand, but that makes it a little harder. So let me grab my graphing calculator real fast. And I'm going to show you how to do that as well. Sorry. Things are popping up on my screen. I do not want popping up on my screen. So we're waiting for the TI Smart View to come up. And we're going to put that equation straight into our Y1. So get out that calculator, and here we go. All right. Let me get this on large screen so you can see better. So it was 30 minus 2x and 16 minus 2x times x. All right. So this is the thing that we're trying to maximize or minimize. So what I really want to do is I want to watch the derivative graph of this. I'm going to do the derivative equal to 0. And in the previous solutions, previous problems we did, we took the derivative. It was very easy algebraically to do that. And but this derivative is a little harder. It can be done. You can pull that out and do all that. But I would like to show you how to do this anyway. So I'm going to go back to, and I did second left. That gets me back to the beginning of the line. And I'm going to turn this guy off. I don't want to see him. I want to see the derivative graph of this. And I want to see where it's 0. So this is the graphing calculator way to do what I did algebraically a moment ago. So I'm going to ask that the calculator math 8, you cannot see that, but it's below there, is the derivative. I'm going to ask it to graph the derivative with respect to x, and I want to do y1 bars, y bars, enter, enter, and there's also a button up here in your alpha thing that you can also use. And then I want to graph for all x. And what this does is it graphs the derivative graph. So I can see where the zeros are. So in Y1, you put the thing that you're trying to optimize, and in Y2, you ask it to draw the derivative graph. Well, I probably need to be in a specific window. I know that I cannot be bigger than, X cannot be bigger than 16 because that is one of the sides. And so if I cut out, actually, I can't be bigger than 8 because if I put an 8 in there, one of my dimensions would go away. I'm looking for a 0, and so my Ymin and Ymax do not have to be large. Matter of fact, I always make them small, -1 to 1. I just want the zeros of the derivative, okay? So the domain, let me say this again, if you cut out 8 inches, that would make your width of 16 go to 0. And so I don't need any more than 8. My Y window is what it is because I'm looking for the 0 on this derivative, so I don't need many Y's. You hit graph, and I want it to be maximum, so positive to negative, and that was kind of fast, but there it is. So there is my little place where I have a maximum. So I'm going, and that's not a nice number, by the way, so it doesn't look like it. So I'm going to do second calc, second calc, I said second, I hit alpha, didn't I, crazy me, and I'm going to hit 0, because I want to find the 0. This 0 is between 1, 2, 3, and 4, so I'm going to hit 3, enter for my left bound, and 4, enter for my right bound, and hit a gas, and it'll tell me what it is. So it looks like 3 1/3 to me, okay? And I'm going to store that into alpha A. Oops, and I don't want to do that there. Sorry, excuse me. I'm going to second quit, and I'm going to store that into alpha A because I'm going to use it in just a minute. Okay. Excuse me. I'm going to go to store alpha A. Let's see if it fits. There it is. Okay. I'm going to use that in just a minute, and so I need to make sure that I store it somewhere, because I'll show you why in just a minute. All right, so that is, so I think 3 1/3 is one of our answers. And so let's go figure out where we are. Okay, so I know that v prime is equal to 0 when x is 3 1/3. 3 1/3. So that's my size of squares that I need to cut out, right? And so I've answered that part. That's my size square, and it is in inches. That's my cutout. So now it says, what is the maximum volume? Well, if we'll remember, when we put that in Y1, Y1 is the volume itself. So I'm going to ask my calculator and go to my home screen, and I'm going to say Y1, bars, Y bars, enter, enter. And I'm going to ask it to evaluate that at alpha A, because that A value is the cut that I need to make. And so the answer that I get is the volume that it produces. So by putting that in there, putting in the volume formula that I have Y1, I will find that volume. So the volume is 725.926. We're going to round. Excuse me. So 725.926. 725.926. 725.926. 6 inches cubed is the maximum volume. All right. Well, I hope this has helped, and we'll come back. We'll come back and do some that are a little tougher in part 2, and hope this helps. Thanks. Bye.